Have you ever stopped to think about why a firework just explodes in a flash of light, but a piece of metal can take years and years to rust? I mean, they're both chemical reactions, right? But they happen on totally different schedules. It's almost like the universe has a speed dial for chemistry, turning some things way up to instant and others all the way down to a super slow crawl.
Yeah, just look at these two. On one side, you've got a firework, a massive burst of light and sound, and it's all over in just a few seconds. And on the other, you have iron rusting. It's this slow, creeping change that just unfolds over months. The difference in their speeds is just massive.
So that's the big question here, isn't it? What's actually controlling that cosmic speed dial? What are the rules that decide if something happens in the blink of an eye or over thousands of years? Well, that is exactly what we are going to dive into. All right, first up, fast lane, slow lane. Let's get a real feel for just how wide this range of reaction speeds actually is. We're talking about everything from the chemical fast lane to the slowest of slow lanes. I mean, the scale is just mind-boggling. You got fireworks, which are done in a flash. Then there are things like making soap, which might take a few minutes. Then you've got iron rusting, taking months. But then way at the other end of the scale, you have things like the formation of oil deep in the earth, and that's a process that takes millions of years.
Okay, so to figure out what controls the speed, we first have to get on the same page about what a reaction even is. So let's quickly run through the basic playbook for any chemical change. Let's make it super simple. Think about making mango juice. The stuff you start with, the mango, sugar, water, that's what chemists call reactants. The actual process of blending it all up, that's the reaction. And that tasty glass of juice you get at the end, that's your product. It really is that straightforward. Reactants react, and you get products.
But what we really care about here is the speed of that whole process. In chemistry, that's called the reaction rate. It's just a fancy way of asking how quickly are your reactants, your mango and sugar, turning into your product, the juice. And this just makes total sense when you stop and think about it. At the very beginning, before you've even hit the on button on the blender, you have 100% reactants, right? You have zero juice. And then by the end, all those reactants are gone, and what you have left is 100% product. We can even picture this on a graph. If you were to track the amount of your reactants over time, you would see a curve that starts way up high and then just drops and drops as those ingredients get all used up. And the products, well, they tell the exact opposite story. Their curve starts down at zero because you don't have any yet, and then climbs steadily until the reaction's done. You start with no juice and you end with a full glass. Easy enough. Okay, so we've got the playbook down. Now it's time to step into the control room. We're about to find out about the 4 main control knobs that chemists, and, well, all of us, can use to adjust that cosmic speed dial. And here they are. The 4 big ones are surface area, concentration, temperature, and these really cool things called catalysts. Let's break them down one by one. First on the list, surface area. Think about dissolving sugar in your coffee. A big solid sugar cube dissolves kind of slowly because the coffee can only touch the outside. But what if you crush that cube into powder? It disappears almost instantly. You've exposed way more surface for the coffee to work on. More contact equals a faster reaction. Next up is concentration. This one's all about how crowded the particles are. It's like the difference between a few people wandering down a quiet street versus a packed crowd in a city square. In that crowded square, people are going to be bumping into each other all the time. It's the same idea in chemistry. Higher concentration means more particles jammed together, which means way more collisions and a faster reaction. Our third knob is temperature, and this is one you use every single day. When you crank up the heat on the stove, what are you doing? You're giving the particles in your food a ton of energy. They start zipping around like crazy, crashing into each other more often and with more oomph. That's what speeds up the reactions that cook your food. And finally, we have catalysts. Now, these are really fascinating. A catalyst is like a chemical matchmaker. It's a substance that grabs the reactants, helps them get together more easily, and speeds up the whole process. But it doesn't get used up itself. It's basically providing a shortcut, lowering the energy needed to get the reaction going and making things happen way, way faster. And that idea of catalysts brings us to the most amazing ones of all, the ones that are working inside your body right this very second.
It's time to talk about nature's ultimate accelerators, enzymes. So, an enzyme is simply a biological catalyst. It's a special protein that nature has designed to speed up one very, very specific chemical reaction inside a living thing. And when I say speed up, I really mean it. You really can't overstate how vital these things are. The chemical reactions that we need for, well, everything, from digesting food to thinking a thought, would be so slow on their own that we couldn't survive. Honestly, without enzymes, life just wouldn't be possible. So how do they pull this off? Well, it's often called the lock and key model. Every enzyme has a perfectly shaped little pocket called an active site, and a specific reactant or substrate fits into that site like a key into a lock. Once it's in there, the enzyme does its thing, makes the reaction happen, and then spits out the new products. Then it's immediately ready for the next one, sometimes millions of times a second. It's just this incredible, specific efficiency that makes them so powerful.
So, okay, this is all cool science, but why does it matter to us? Well, it turns out controlling these reaction rates isn't just for scientists in a lab. We do it every single day to shape the world around us.
Seriously, think about it. Cooking? You're just using heat to speed up reactions. Putting leftovers in the fridge? You're using cold to slow down the reactions that make food go bad. That catalytic converter in your car uses a catalyst to quickly change harmful exhaust into safer gases. And of course, your own body is using enzymes at this very moment to digest your last meal at lightning speed.
So the speed of the chemical world isn't just some random mystery. It's all governed by a set of rules, a set of control knobs that we now understand and can actually turn. And that leaves you with a pretty exciting thought. As we get better and better at this, what other reactions will we learn to control? What will we be able to speed up or slow down in the future? The possibilities, well, they seem pretty endless.